let's do a physics experiment with the Vernier Go Direct sensor cart and the fan. And this is an experiment I'm going to have my students do, so don't look at this if you're my students. And I think there's going to be a surprise. But I haven't done it, right? So this is all brand new. It's a brand new world. So let's just get to it. So what I want to do is to turn on this fan, and it's going to have, I assume, a constant force. And then I'm going to let it accelerate. I'm going to find the acceleration. And then I'm going to change the mass. And then I'm going to do it again. And then I'm going to change the mass. And so let's look at what I have on the board here. So here's my cart. Here's a force diagram for my cart. And in fact, I think I'm going to have it go this way, but it doesn't really matter. So there's a force. I'm just going to call it F for now. That's from the fan. I have the normal force, the gravitational force. Those two have equal and opposite directions of y component forces, so that the net force in the y direction is 0 and the cart doesn't move up and down. And in the x direction, I have just that one force, and that's going to be mass times acceleration in the x direction. Now, what I'm going to do, if I assume that force is constant and I change the mass, it's going to change acceleration. So I have two variables that are changing, and I want to make a linear graph. So how do we make a linear graph in that case? Well, I can solve for the acceleration as the constant force times 1 over the mass. And that tells me what to plot, right? Because let me put this on the board. This is like, and this is the thing that my students have trouble with, y equals mx plus b. So if I plot 1 over m on the horizontal, if I plot acceleration on the vertical, then the slope should be the force, the constant force. It should be a single constant force. Okay, so before I switch over to the computer, I have my masses that I'm going to change. I measured the mass of the cart. I measured the mass of the fan. I added them together. So that gives me the mass of 0.436 kilograms. And then I can add these 125 gram bars, bloop, right there, and change the mass. So I can get multiple different mass measurements. If you use no extra masses plus 1, you could get 5 different measurements. That's pretty good, but I'm actually going to do 6 because I'm going to do one more to load up even more mass. Okay, let's jump over to collect data. So the first thing I need to do is to turn on, oh, it's already on. That little light's blinking. Okay, so it's on. And now I'm going to switch over to the computer. Here we are. And I'm using graphical analysis. So let's just review how do we collect data from this sensor. Because the cart has a wheel in the bottom that measures position, and that's what we're going to use to measure the acceleration. Now, there are a lot of ways you could do this experiment, right? You can measure the force other ways, but let's just do it this way. So I'm going to go up to sensor collection right there. And I want to connect it to this card. Notice it says 7K6, and well, you can't see it. It does say 7K6 on this too. And everyone, G means green. It's a green cart, which is super useful. So I'm going to click connect. And now up here, this is something that's important for later, but not today. It's connecting. No, it's not. Did it turn off? I think it turned off. Turned it back on. It timed out. Okay, there it is. Now, the sensor channels, if I click this little thing right there, I can collect position data, which is what I want. It also has a force sensor. It has an accelerometer in there too. But let's just use the position data for now. So I'm going to say done. And then it comes up with this. It shows 2 graphs. I really don't want 1. So let's just switch that to 1 graph right there. Okay. So there's my data. And it's going to collect data for, down here, the time-based data for 5 seconds. That's how long it's going to collect. And you could change that if you want. 5 works out fine. Okay, let's just get to it. I have over here my cart, my track right there. And you can't see it, but there it is. And it's very flimsy because I wanted to be able to have it in the frame. Let me just switch over to the camera so you can see what it looks like when I collect data. So I'm going to collect data. The cart's going to be, the fan's going to be pushing it this way. I already have it set on force setting of 1 for a time of Hold that button down and it switches to the time. I have it for a time setting of 2, which is 3 seconds. Okay, so that should be good enough. So what I'll do is I'll put my card over here. I'll press the start button. It gives you a little blinking time starting, and you catch it. Okay, so that's what I'm going to do because I don't want it to go off the edge. And as I add more masses, it's not going to go as far because you'll have more mass. Okay, so let's switch over to the computer, and this time we're going to collect data. Okay, here's my data. I'm going to click the start button on the fan first because it has time, and then I'll click the collect button on the computer. I missed it. I got enough of it. But let's do it again because I wasn't very good. I wasn't ready. Okay. Start, collect. Okay, and I stopped it. You saw that. And I said it wasn't perfect. Okay, so how do we get the acceleration from this? Now, you can see right here where it starts to accelerate, and that is a parabola, and you could fit a parabola. I personally like to use the velocity graph just because it's easier for students to visualize what's going on. So let's go over here and switch this to velocity and turn off position. And now you can see that doesn't look right. So here it's accelerating. Oh, I guess it's just that part right there where it's accelerating. Is that right? I think I better do it one more time. Doesn't matter, right? I can do it one more time. So let's do it. Actually, is that data set 1? That's why. Okay. That's better. I was on the wrong data set. Okay, so there's my cart. It was sitting there and then it accelerates. And since we're looking at velocity versus time, and acceleration is change in velocity divided by the change in time, that's the same as the slope of a velocity time graph. So I'm going to highlight this region of data, and then I'm going to apply a curve fit, and I want linear. And then it gives me a slope of 0.2619. And I'm going to write that down on the board right up here for that mass. 0.2, what did I say? 2619. See, I'm taking data just like a normal lab. Okay. Now I'm going to add 125 grams to my cart, and I'm going to repeat the measurement. So up here, I'm going to click, and this is a little tedious, and I know, apologize, but that's fine. So click that, and then click collect, and then here we go. Oh, it hit the thing. That's funny. It's fine. Okay. So now I know what to do, right? I'm just going to highlight the region, and I'm going to apply curve fit, linear. See, I can collect data very fast. And I get 0.2053. 0.2053. Now let's add another bar. And if you're getting bored, just skip to the end. I don't mind. It won't bother me. And in fact, I wouldn't even know. Okay. Okay, here we go. Press that button. Press this button. Apply a curve fit. Apply. And so I could just do this beforehand, but I don't know what's going to happen, and that's why I'm doing it live. And here I get a 0.1689, 0.1689. Now let's add another bar. Now, you have a whole bunch of things like it's possible that the battery could be dying and the force could be changing on this. And I'll show you some other things in the end. So don't get too excited because we're going to do some other cool stuff here. Don't get too bored either. Apply. I got 2 more data points. So this is 0.143. And then, yep, another bar. Click. Click. And I did show you this, but if you want the old data, if you click this, it has all of that data on there, right? It shows you just the last set, but it's all still there, which is super nice. Okay, so I'm going to highlight this, apply a curve fit, linear, and this is going to be equal to 0.1171. Now, I'm going to do an illegal move. I'm going to add 4 more. So that's 500 grams, 125, 250, 250, 500 grams. So I'm just going to jam it up here on the front of the cart. And let's just see what happens. Okay, it's not perfect, but it's fine. Okay, click collect. Okay, let's take that off. I don't want my cart to fall. See, it's going to roll away. Okay, what is the acceleration? I'm going to highlight this area right there. Apply a curve fit, linear, and I get 0.0711. 0.0711. Okay, so now we need to make a graph with the 1 over the mass, which I should have already calculated, 1 over the mass on the horizontal axis and the acceleration on the vertical axis. Okay, so I don't actually know how to do this without starting again. So let's just see if I can do it. New. Can I create a new manual column? Well, let's just start over, right? New experiment. And I'm not going to save it because I don't really care. I don't save. That's fine. And then I'm going to go with manual entry. Okay, now I'm pretty sure I can do this. I haven't done it, but I'm pretty sure I can. So let's go up here and let's call this mass. Column options. Let's call it mass in units of kilograms. And then this is acceleration. In units of meters per second squared. Good. Okay, so now I just need to enter my data. It's right behind me, 0.436 and 0.2619. Again, if I wanted to make this exciting, I could do it before. But again, I don't know what's going to happen. I can't do it. 0.561. That would ruin the suspense because I don't know. 0.2053. 0.686, 0.1689, 0.811, 0.143, 0.936. And you'll notice it's plotting it, but it's not what we want. 0.1171, 0.1171, and then finally 1.436 and 0.0711. Okay, so I want 1 over the mass. I think I can do this. So if I go up here to data set and I go do, no, I don't want to do that. I want to do this. No. New calculated column. Add calculated column. Okay, so I want to calculate this. I'm going to call this 1 over m, and it has units of 1 over kilograms. And I'm going to insert an expression. Whoa, I hit my thing. See, caught it. And it's going to be a over x. Let's try that. A over x, where the parameter a is that, and this is mass. Okay, that did it. Apply. Okay, great. Now I want to change this to acceleration and this to 1 over the mass. And there you go. Look at that. That's a pretty nice linear graph. Let's go ahead and fit a linear function to this data and see what we get for the force. Okay, so I think I can go to, I want the whole thing. apply curve fit. There, this right down there. Apply a curve fit. I didn't want to hide. I didn't need to highlight anything, and I want to do a line right there. Okay, so there you go. So this says that the one, it's linear, and that's pretty good. Two, the slope is 0.1193. So that would be the force that this card exerts. 0.1193 meters per second squared per kilogram, 1 over kilograms, which is a kilogram meter per second squared. So that is a Newton, right? That is the force in newtons. Now, I'm not going to do this, okay? But what you could do is to take the cart and then allow it to push against the sensor and see what kind of force you get there too. I'm going to do it, actually. And then I want to show you something, because I thought this would turn out more poorly, in particularly for this data point down here, which is the largest mass, because it's 1 over the mass. As you increase the mass, you also increase the frictional force, right? If we talk about a cart rolling down an incline, it doesn't matter what the mass is. But when I have an external force, it does matter what the mass is, because as you add more and more mass, you increase the normal force, which increases the frictional force. So if I loaded this thing up with a whole bunch of mass, I think I would notice a difference, because the friction force would increase, whereas the fan from the force, the force from the fan does not increase. Okay. So let's do two things. I want to show you this frictional force, how we can see that it is indeed there another way, and then we'll measure the force too. So I'm going to do another new experiment. I'm going to save this one just because I do like it. Save as. I shouldn't have done that. Okay, let's say force 1. I don't know. Okay. Now I'm going to go up here to new experiment, and I'm going to connect back to the sensor. Sensor collect. Oops, I didn't do that. So I forgot this before. So if I go over here to that little thing, I can change this to, I can change what I collect, force also. Okay, so now I have force. And let's make this 2 graphs. And so the first thing I want to do is collect force data. Now down here you'll see that the force is already at 0.12 newtons. So that's not good. Oh, you can't see that because my big fat face is in the way. But it is down here in the corner. So I can click that and then go to 0. You could calibrate it too, but I'm not going to. Now, I do need a way to have something push against it. And I don't have the sensor. I don't have the little, let's see this. I didn't think this through. Okay, let's put this piece of chalk right here. I'm going to put that piece of chalk just so I can push the sensor. That's a bad idea, right? Okay, I'm going to hold that like that. Now I'm going to collect data, and I'm going to turn on the force sensor, and we can see what it reads. Oh, it didn't collect. Okay, never mind. I got to turn that on. Okay, there we go. So it's going to push against that little piece of chalk. And then, oh, I did that wrong too. Stop. Collect. No, I did it again. Stop. Click this first. Then click collect. Okay, so this says a force of going down here. This is the force on. I'm going to highlight that region, and then I'm going to go to view statistics. Now give me the average. This says the average, the mean is 0.155. So, I mean, it was pretty close. We had what, I already forgot. But that's another way you could do it. You could do a much better experiment than that. I just came up with that just at the time. Okay, I want to show you the frictional force, how you can see that. Let's go back to 1 graph because I don't want 2 graphs. And I'm going to plot velocity, not the force. Now, what I want to do is to take my cart, and let's switch over to the camera right here. I'm going to show you the first without the thing. So the fan is pushing this way. So what I want to do is to take the cart right here, turn on the fan, and push it that way. So now the fan's going to slow it down, stop it, and come back. Okay, so let's see if we can do that. I'm going to click start. Okay, so why does that matter? Because when it's moving this way, the fan's pushing this way, and friction's pushing that way too. But then once it starts coming back this way, the fan's still pushing that way, but now friction's pushing that way. So we should see a difference in the slope of the speed of the velocity graphs. Let's see if we can collect data and see if that works. So I'm going to click collect, I'm going to click start, and then I'm going to click collect. Start, collect, collect. Okay, I didn't get perfect data. Let's try it one more time, and I didn't even show it. Okay, so let's switch over to the computer. I'm going to get ready to click collect. So let's say start, collect. Okay. Now you can see that right here. So here's the way it was moving where they were in the same direction. Let's fit a function there, apply a curve fit, linear, and that's my slope. And then over here, it's on the way back, and they're acting against each other, right? Friction and the fan are against each other. So if I apply a curve fit, linear, I get two different accelerations. Now it's possible, I'm not going to go through the details right now, but you can see that they're not the same, right? I have 0.2226 and 0.1355. So the reason they're different is because of the friction force. Let's actually do this one more time. I'm going to take off the extra mass so it's not heavy, and let's just see. So that's a difference of, about 0.1 meter per second squared. Let's repeat that experiment without the mass. So I'm going to go up here, finger over the collect, click, collect. Oh, it came off the track. Sorry. Okay, let's try it again. Finger over the collect, click, collect. It gets a little wobbly, but you'll notice here that there is not as large of a difference because, again, friction is not as much because the mass is lower. Apply curve fit, linear. Apply curve fit, linear. So here I get a 0.3766, 0.2819. So that's less than 0.1 meter per second squared difference. So the frictional force is indeed less. It is small, and I'm not using the best track. I'm using this cheap old plastic track. I think if you use a nicer track, it'd work even better. But there you go, playing around with the force data. I'm actually excited. Students are going to be able to do force, mass, acceleration data. That's what I want. It's going to be great. And there you go. Hope you learned something I did. I'll talk to you later.